Hello everyone, today I'm going to present our work in INFUSE Invisible Plausibly Deniable File System for NAND Flash. This is a joint work with my colleague Aaron and my advisor Radu. Nowadays, we are storing all kinds of personal data in our storage devices, such as laptops, smartphones. The sensitive data we stored in our device should be protected from adversaries who want to have access to those data, so we need to have storage privacy schemes. Of course, we can use disk encryption to protect those sensitive data stored in our storage devices. However, sometimes encryption is not always useful because the adversary is too powerful. Some adversary in real life is so powerful that he can ask the users to give up the encryption keys. In these cases, encryption cannot protect our sensitive data anymore. Here are some examples where users come across such powerful adversaries, such as some government. And we can see a lot of cases reported by the users who was forced to give up their encryption keys. So we need something more than conventional encryption to protect our data. Plausible deniability is such a tool that can help us to protect our sensitive data. Plausible deniability is a security property of a mechanism that allows parties to claim to others that some information is not in their possession or that some transaction has not taken place. People have designed several PD schemes. Now let's see how those existing PD schemes works. Currently, people design PD schemes with two modes, the normal mode and the PD mode. A user who uses a PD scheme should make a choice about which mode to use. When he chooses to use the normal mode, he is allowed to store public data in the storage device. While a user is choosing the PD mode, he is allowed to store both public data and hidden data in the storage device. A PD scheme helps the user to hide which mode he is choosing to use, so the adversary cannot know whether the user has stored any hidden data in the storage device or not. All current PD schemes work under an assumption that it should be convinced that users can use a PD scheme in the normal mode. However, this assumption is sometimes not that convincible, as a PD scheme is designed for a user to hide the existence of some hidden data. So when an adversary observes that a user is using a PD scheme, the adversary will believe with a high probability that he is using the scheme in the PD mode and some sensitive data is hidden by the user. So can we hide the existence of the two modes in a PD scheme? Or in other words, can we have some PD scheme that his deployment of the scheme can be hidden from the adversary? This is the topic we want to focus on in this work in INFUSE. How can we hide the deployment of a PD scheme? Let's see a simple example here. Assume that we have a PD scheme, which is a file system who has also two modes, the normal mode and the PD mode. Besides, we have another of the shell file system here. More importantly, we assume that the normal mode in the PD scheme have the identical layout as the of the shell scheme. As the PD scheme ensures that the adversary cannot distinguish whether a normal mode is used or a PD mode is used, and the normal mode has the identical disk layout as the of the shell file system, then the adversary cannot distinguish whether the PD scheme is used or the of the shell file system is used. We call this kind of PD schemes as PD schemes with compatibility. Now let's see what will happen if a user is using a PD scheme with compatibility and how this kind of PD scheme with compatibility can hide not only the existence of hidden data, but also the deployment of the PD schemes itself. Here we have a user who is using a PD scheme with compatibility, and he has some public data and hidden data to store in the storage device. Then he stores his data with his public key and hidden key to the storage device. When an adversary has access to the same storage device, he will ask for the encryption keys from the user, and the user will give the adversary the public key, and told the adversary that an off-the-shelf file system is used. With the public key, now the adversary can get the public data from the storage device by reading it as an off-the-shelf file system. However, the adversary has no way to know that user is using a PD scheme and the user has stored some hidden data in the device. Among all those existing PD schemes, there is one PD scheme called StackF, which is claimed to be compatible with a file system ext2. However, this StackFS is not a PD scheme with compatibility, as it needs to store some metadata, which is a bitmap, in the storage device. The existence of this bitmap will reveal to adversaries that the user is using the StackFS rather than a ext2. As we mentioned before, a PD scheme with compatibility should have the same layout as another off-the-shelf storage scheme, which means that no metadata is allowed to store in the storage device for the hidden data. This seems to be hardly possible. However, NAND Flash provides us such an opportunity because it provides us some hardware-based out-of-band storage capacity. Before going into more details, let's see what is a NAND Flash first. NAND Flash is a storage media consists of arrays of NAND Flash cells. Those cells are grouped into pages, and pages are grouped into several blocks. A page is the smallest unit for a write operation in NAND Flash, and a block is the smallest unit for an erase operation in NAND Flash. Different digital bits are stored in NAND Flash cells by changing the gate voltages of each cells. In a write operation, the NAND Flash cells are charged and the gate voltages in those cells increase. While in an erase operation, the gate voltage in cells decrease to 0. As we know, the gate voltage is an analog signal. In order to represent those digital bits, we need another thing called the reference voltage. So a cell with a gate voltage that is larger than the reference voltage is set to store a bit 0, while another cell with the gate voltage smaller than the reference voltage is set to store a bit 1. Two special techniques help hiding extra bits in NAND Flash. The first one is partial programming. Partial programming allows us to increase the gate voltage of the NAND Flash cells gradually so that we can set its gate voltage to the value we want it to be. Another technique that helps is called the read-retry. It allows us to adjust the reference voltage and read different bits from one cell. Let's see a simple example here. We charge a cell with partial programming to have some gate voltage we want. With the original reference voltage, this cell is set to store a bit 0 as the gate voltage is larger than its reference voltage. However, when we change the reference voltage to be larger than the gate voltage we charge it to be, this cell is set to store a bit 1 now. Of course, we can decrease the reference voltage so that this bit store a bit 0 again. So by charging the NAND Flash cells with partial programming properly and changing the reference voltage with read-retry, we can store more than 1 bits in one NAND Flash cells, and this provides us extra storage bits in NAND Flash. As we can see, in order to store extra bits in NAND Flash, we are changing the gate voltage in NAND Flash cells. And this kind of change may lead to the fact that extra bits are stored in NAND Flash device. However, this kind of voltage changes can be covered up by the inherent variation of the gate voltage in a NAND Flash device. As we can see in this figure, the distribution of the voltage for the cells in one page is shown here in this figure, and we can see that for these 4 pages, the distribution actually varies a lot. This kind of variation in the gate voltage is because of several reasons, such as the programming, the retention, and the manufacturing process. And this is unpredictable. So when we are storing our out-of-bound storage bits in NAND flash, it will change the gate voltage, but it will change the gate voltage under this variation resulting from the inherent factors. In this case, the adversary will not know that the change of the voltage is because of the inherent variation, or it's because we are storing extra out-of-bound storage bits in the disk. Although the voltage variation in NAND flash device allowed us to store extra bits in NAND flash, this is not enough for us to have a PD scheme, as we need a way to organize all those out-of-bound storage bits in NAND flash to be the valid data in the user space. And this is not a simple task. Here we list a few challenges we are facing when we want to design a PD scheme based on the out-of-bound storage bits in NAND flash device. First of all, we need to hide the hidden bits embedding process described above. Secondly, we need to hide the file system metadata that is required for the hidden data. Thirdly, we need to decouple the file system operations from the hidden data so that the existence of hidden data doesn't change the original file system operations behavior. And we need to ensure the hidden data integrity as well. And most importantly, we want it to have compatibility, which means it should have the same layout as another of the shell file system. Based on the bit hiding technologies we described above, we designed INFUSE, a file system for NAND flash that is compatible with INFUSE. It allowed users to store both public data and hidden data in a NAND flash device. The public data is stored in the original capacity, and the hidden data is stored in the out-of-bound storage bits. INFUSE have the same layout as the INFUSE, and INFUSE requires an unmount operation before the adversary can see its disk layout. Now let's see how INFUSE is designed in details and how those challenges we mentioned before are solved in INFUSE. First of all, INFUSE is built upon an intermediate layer above the physical layer of a NAND flash device. We randomly select physical cells to store extra hidden bits, and we organize those hidden bits as hidden pages in the intermediate layer. As both the public data and hidden data are encrypted, and the cells that store hidden data is randomly selected, the adversary has no way to know the locations where the hidden bits are stored. In this way, we use the virtual hidden pages and the intermediate layer to hide the hidden bit embedding process. Besides, INFUSE has a directory structure which has minimized the interference between the public files and the hidden files. As shown in this figure, we can see that all the public files has public parents and all the hidden files has hidden parents except from the root. By separating the public files and the hidden files under the directory structure, we can ensure that the public file is not affected by the hidden traces. Moreover, we also store the metadata for the hidden files in INFUSE in the out-of-bound storage bits. In this way, since the adversary cannot know whether there is any hidden bits stored in the out-of-bound storage bits, they cannot detect the existence of hidden data by looking for the metadata for hidden files. So we can hide the file system metadata. What's more, we successfully decouple the original file system operations from hidden data by carefully designing the page allocation scheme in INFUSE and designing the garbage collection that is not affected by the existence of the hidden data. These figures here shows the block state transitions in INFUSE. The 5 states in yellow are shared by both INFUSE and INFUSE. In INFUSE, an empty page can be allocated and goes to the allocating state. And then when array pages are written, it goes to the for state. And when garbage collection happens and a block is selected as a garbage collection victim block, the page state is changing to be the collecting state. After garbage collection, the pages can go to the dirty state, and it can be erased so that the page goes back to the empty state. In order to not interrupt the original block state transition, we require that only pages in full state can be allocated for hidden bit write. What's more, whether a block should be garbage collected in INFUSE has nothing to do with whether any hidden data is stored in that block or the state of any hidden data in the blocks. Except from all the three mechanisms we used in INFUSE to solve the challenges we mentioned before, we also have some other mechanisms which is detailed in the paper. Another thing we want to mention is the hidden data storage capacity in INFUSE. As we already said, store hidden data inside the NAND flash need to change the voltage of the cells. The more hidden data that is stored in the device, the more obvious the changes are. The hidden data capacity is related to a lot of factors. First of all, it's related to the accuracy of the hidden bits programming. In other words, the more accurate we can set the voltage to be with partial programming, the more hidden data we can store. The other factors that affect the capacity is the read and retrieve capabilities that is supported by the NAND flash device and the reference voltage levels that is supported by the hardware. In order to evaluate the performance of INFUSE, we benchmark both YAPS and INFUSE with FileBench. The result is shown in this figure. Note that the y-axis is the log scale. We can see that accessing the public data in INFUSE is around 50% slower than the baseline YAPS, and access the hidden data inside INFUSE is around 30 to 40 times slower when compared with YAPS. Note that this number is get when a hidden page is spread across 16 physical pages. Actually, when the number of physical pages needed for a hidden page is changed, the performance also changed. We do a series of experiments and choose the relationship between the throughput of INFUSE and the number of hidden pages in each physical block. The results are shown in these two figures. The left figure shows the throughput for accessing the public data. It can be seen that the throughput increased at first, then decreased a little bit when the number of hidden pages per block increases. So it seems that under our setting in the experiment, storing 2 to 4 hidden pages in one physical block leads to the best public performance. For the performance to access the hidden data in the INFUSE, the figure in the right shows that the throughput increases when the number of hidden pages increases in each physical block. This is quite reasonable as the more hidden pages there is in one physical block, the less number of physical page operation is needed to access a certain amount of hidden data. To conclude, INFUSE is an invisible file system that provides plausible deniability for NAND flash device. Here, the invisible means that it has the identical layout as a standard file system YAPS. INFUSE is designed based on a hardware-based hidden bit embedding scheme in NAND flash. INFUSE stores hidden files in the out-of-bound storage bits in NAND flash so that even the multi-snapshot adversaries who can access the NAND flash device several times cannot detect the existence of the hidden data and the use of INFUSE. And INFUSE also provides redundancy, handles overwrites, and survival data loss. Thank you.